Okay, so let's keep going down this delta G rabbit hole. Okay, and I want to derive a special relationship dealing with free energy and keep chemical equilibrium. So we're going to connect some big picture ideas that we've been talking about all semester. So I'm not going to go through the full derivation. So that's why it says it can be shown with lots of calculus and physics. We get this equation right here. Okay, where this delta G, that is our delta G for, let's say, the entire process, or we could really think of that as like the total change in free energy. My G standard value, right? That is my free energy of my system. So we'll just write system. And then that's plus RT natural log times pressure, okay? And this is derived for gases, but we shall see that this relationship that's going to manifest, you can take out all this blank white space here, this is going to be applicable to also liquids and solids. Okay. So I'm going to start filling out this reaction for this specific reaction so you can see where I'm going to take this. So for example, I could write the Gibbs free energy for the nitrogen molecule for this entire thing. And that would go as the following: G into, which equals G standard into plus RT times the natural log of the partial pressure of N2. So that's how these kind of equations work. We start putting in specific things for these molecules. And so let's do it for everything else. So I could do the same thing for hydrogen. And let's write that all out. I'm going to try to write this as carefully as I can so it's nice and legible. Okay. And then finally I can do it for the ammonia, NH3. Okay. And soon we'll see the difference between these two G's. Like, why do we have two of them? If you're confused by that, I understand. We're going to see what happens to those quantities in a moment. Okay. So now if I wanted to get the delta G, and again, I want the delta G for the entire process. And what I mean by that entire process is when this chemical reaction happens, so obviously there's going to be chemistry, but there's also going to be a change in pressure. There's going to be a change in volume. There might even be a change in temperature if it's an exothermic or endothermic reaction. So really this G is telling us like the whole process, not just the chemical reaction. Okay. So if I wanted to get delta G for this entire process, we recognize that that's going to be the sum of the products minus the sum of the reactants. So same thing that we did before. And not only is that the sum of the products minus the sum of the reactants for the chemical part, but also for the physical part, which is this RT-LNP. Okay. So I could just write that simply as 2 times G NH3. And now because I've got 2 NH3s in my reaction, right? And when I say 2 times G and H3, I really mean 2 times this entire equation, okay? And now that's minus the sum of the reactants. So that's going to be 2 times the free energy for nitrogen plus 3 times the free energy. Oops, let's write G there. 3 times the free energy for hydrogen. And so now I'm going to plug in all of this stuff into this equation, and we're going to see something magic happen, okay? So now I'm going to have, so I've got 2 times G and H3, so let's write that whole thing out. So I'm going to have 2 times standard G of NH3 plus, and I'm just going to distribute that 2 all the way through, plus 2 times RT natural log of the partial pressure of nitrogen. Okay, good. And then now, so there's a negative sign there, so let's keep that negative sign. Okay, so we're summing up my reactants. So now that's 3 times G standard for H2 plus 3 RT natural log of PH2. So there's my sum of my reactants. And then now I've got so that was the negative part for the reactants. And I'm writing this kind of backwards order. Apologies for that. So I'm just going to say 2. Oh, I know what I did. So let's, here we go. I'm just going to erase this, and I'm going to erase the negative sign. I was talking and writing at the same time. Let's just start this over a little bit. Apologies there. So I wrote 2NH3 and then I wrote 2NH2, and you might be like, what the heck is he doing? Okay. NH3. Okay, so we've just done this first part. Okay, apologies for the confusion there. So now I'm going to say minus the sum of all of my reactants, which is going to be 2G N2 plus 2RT natural log of P N2. And then now that's plus 3, and that's my standard G, right? Standard G, H2 plus 3RT natural log of PH2. And let's see if we got all that right. So we've got 2 times the standard free energy for ammonia plus 2RT LNP NH3. So the 2 came from the stoichiometry in the reaction. And now that's minus 2 times the free energy for nitrogen right here, and 3 times the free energy for hydrogen right there. And so now what we want to do is collect like terms and do a little bit of algebra. So I'm going to collect all the standard G's, okay? And I'm going to write those as 2 standard G of NH3 minus 2 times standard G of N2 plus 3 times standard G of H2. So, and I'm going to cross things out as I use them here, just so I recognize that I took care of them. So I used this, I used this, and I used this, and I collected them all like so. Now I want to collect all of my RT values, okay? And so I'm going to do a couple tricks. So I'm going to keep this all blocked together. And then now down here, I'm going to say plus RT. And so I'm going to factor out RT out of all of these expressions. Okay. So now I factored out RT here. So let's do a bracket. And now that becomes 2 times the natural log of the partial pressure of NH3. And now that's minus 2 times the natural log of the partial pressure of N2. And we'll distribute that negative sign through, minus 3 times the natural log of PH2. Okay. So we can keep making some simplifications here. And one simplification that I can make, so let's make sure that we've crossed everything off. So now I've used this, I've used this, I've used this, and yep, I've used everything. So now I recognize that this whole quantity is the same thing as my standard free energy of reaction. Cool. So I'm going to replace all of this stuff with just delta G of reaction. And we recognize that all of that equaled the total delta G in the first place. So we're starting to see this equation is manifesting very similarly to how it was written originally, right? Delta G equals standard delta G. Delta G equals standard delta G of reaction, okay? Now I have this plus RT, okay? And then I got all of this stuff, natural log of PNH3 times 2, natural log of PN2 times 2, and so forth. And I'm going to remind you there's a special log trick. If I have, and that log trick is the following, A times the natural log of X equals the natural log of X raised to the A power. So that's another one of these log tricks, okay? So you'll notice here that I've got 2 times the natural log of P and H3. So instead, I can write that as the natural log of P and H3 squared. And then that means I can also write this as the natural log of Pn2 squared. And then this is the natural log of PH2 cubed. Well, there's another log trick I can make. And that other log trick, right, is when I subtract logs from each other, it's the same as dividing them. So check this out. This is pretty cool what ends up happening. Delta G equals delta G of reaction plus RT times the natural log of all of this stuff, which just ends up being PNH3 squared over PN2 squared times PH2 cubed. And I'm going to box all of this off. This was the whole point of making you watch this whole derivation. If we stare at this for a minute, think about what all this stuff is. Ammonia squared divided by nitrogen squared times hydrogen cubed. That's the equilibrium constant. Pretty sweet, okay?